a classic problem that came up when Newton and others were first studying calculus was how to find the value where a curve crosses the x-axis. Now, this problem had existed even before calculus was invented by Newton, Leibniz, and others. But with calculus, we determined a way to add to those techniques, to make them richer. And so one of those was, okay, well, what if I just approximate it with a tangent line? So if you think about this, this makes logical sense. If a curve is going downward and you take its tangent line, then if it were going down kind of like a line, then the tangent line would shoot directly and strike the x-axis at the same point the curve is. However, what we know is that, unless that curve is actually a line, the chances that it'll end up striking at the projected location of the tangent line are not very good. However, it's a pretty interesting technique because if you think about if I started right here and I projected, I wouldn't be that far off from that zero or root of the function. One of the reasons we call those roots of a function is one of the classical things that were studied was something like, if I say x squared minus 2 equals 0, we know that that answer is the square root of 2, that x would be the square root of 2. So the root of the function, we want to find where that value actually is, what the numerical value of that is. And we know that's an irrational number, but we can approximate it very well. So what you do is you take some point on the curve. It doesn't really matter where. However, generally speaking, it's a good idea to kind of have a close enough guess. You don't want to guess 10,000 off because it'll take forever. And then you take the tangent line, so you find the derivative at that point. And then what we're going to do is project that tangent line all the way to the x-axis to try to solve for what the x value is. So to do that, we were going to use what's called the point-slope form of a line. If you remember, that's y minus y1 equals m times x minus x1. It's the same format as mx plus b, but it's been kind of hidden inside it. Like you don't have a b, you have the actual outputs of points on the line. So if we have this point, we know the point's on the line. So if we pick some x value, we'll call it x1. And then we know the y value because that's just the function value at the point. And we can find m because that's the derivative of the function at that point, right? Because that's the slope of the tangent line. We now have three pieces, and this y and this x are the missing pieces. However, so yeah, we can rewrite it like this. So we have this y and the x. Those are still our missing pieces. But what we're trying to do is we're trying to solve for where y is equal to 0. So we actually already know what the y value on this line is supposed to be. The y value is supposed to be 0 because it's striking the x-axis. So really we just have this equation. Well, what does that allow us to do? Well, what that says is I can find the x-coordinate of where that strikes. I can say, oh, well, if I divide by f prime and then I add x1 over, I get this equation. Now, what you'll notice is you're dividing by f prime, so you don't want to use critical points, right? Because A, f prime doesn't exist at a critical point. But B, if it's like that maximum minimum, the derivative will be 0. And that makes a lot of sense. Think about this projection of the tangent line. If you do it at this critical point here, it's just going to project a flat line. It's not ever going to strike the x-axis, so it's not useful to you anyway. So just make sure that you don't accidentally plug in a critical point there. So once you have this, you can now generate what your guess is for that point here. Now, often it's not going to be good enough. You're going to project it and you're going to go, okay, well, that's better than what I had because I had no idea what it was going to be. But then I can say, okay, well, if this is my new guess, then what you really could do is you could come down here, and then you could project it again with this tangent line, and then project it again with a tangent line. Right? You iterate on that process. You say, okay, well, that wasn't good, but I'll call that my, this is my first guess. This is my second guess. And the way you check is you just plug it into the original function. You know the function. If you plug it in, if you plug in x2 to the function, you don't get 0, you actually get this value. Once you get to the x and input here, you plug it into the function, you get this value. And then you project it again, and you get pretty close. So you just keep iterating the process. So you have the initial guess, and then you have the new guess you generated, and you plug it into this thing. The next guess generated, and then there's this general case. This is what's called an iterative formula. And what we're going to define this as, this is going to be a sequence, and we're going to show that sequence can be convergent under some assumptions. Actually, we're not going to show that, but it's true. Under some assumptions, you can guarantee it'll be convergent. But under some other assumptions, you can actually you can get further away, because it can depend on the curvature of the function. You can end up getting a point that's actually pretty close, but because of the way the curvature is, it projects that line really far away. And if you have some sort of symmetrical behavior, it may never actually converge, or it may converge really slowly. And one of the reasons we teach this isn't because it's the most effective method. In fact, there are many more robust methods for root finding, but this is a very classical one, and many of the methods that came after this used this as a template. So it gives you an understanding of what the techniques are now, why they exist, and where they came from.